In section 5, we're just real quickly going to talk about water. We know its structure, but we'll talk about that in the hydrogen bonds. The different properties that make water unique. And then, if we have time, we'll calculate the amount of energy absorbed or released. It's like the one math problem in this chapter, and I don't even really test you on that. The test is just basically going to be a lot of terms, and you'll have to recognize the phase diagram and all the different points like you did in the lab. But the structure, we know this. Water consists of 2 hydrogens and 1 oxygen. They're polar covalent bonds, meaning one side has more of a positive charge, the other side has more of a negative charge. And then the hydrogen bonds are between the molecules that link them together to make them stronger, giving water all those properties like cohesion, adhesion. What else? And we'll talk about this more too, but how it takes so much energy to melt it, boil it, etc. To melt ice, boil water. The number of linked molecules does decrease when I increase the temperature, so that temperature increase will reduce those hydrogen bonds a little bit. And we're going to look at this with ice. Because of those hydrogen bonds, we see basically a crystal forming when water freezes into ice. You see that hexagonal shape because the positive ends of the water molecule are wanting to attach to the negative ends of other water molecules, and you build kind of like a unit cell that multiplies across as it forms that crystal shape. And notice, too, how there's all those pockets of space in between, allowing for water to expand when it freezes. Most materials will contract, get smaller as they hit their solid state, but water is one of the few that actually expands, and that thus makes it less dense than liquid water. And fish that live in cold areas are very thankful for this, because think about it, what would happen if ice sunk when it froze? It would fall to the bottom. If the surface was freezing, it would fall to the bottom, and then that ice would freeze, and then that ice would... You'd have a big chunk of ice in bodies of water, but because the surface level freezes and it floats to the top, you have ice on top that it really insulates the water underneath to allow aquatic life to live in cold areas. Otherwise, they wouldn't be able to, because in the winter, if water was more dense, it would sink. Or if ice was more dense, it would sink in the water and it'd be hard to live there. But all that to say, again, just remember, liquid water is denser than ice. Like if I had a solid chunk of iron, it's going to sink in molten iron. Most solids will do that, but water actually floats to the top when it's solid. Again, just remember, temperature helps to break those strong hydrogen bonds that you see in water. We talked about this diagram yesterday, but just to remind you, as I add heat, this going left to right is adding heat. So when I have solid ice, the temperature rises, temperature rises, temperature rises. Then I hit the melting point. That's that heat of fusion. So all the energy, instead of raising the temperature, the energy goes into melting the ice. Then as I add more heat, it raises the temperature from 0 all the way to 100 degrees. And then no more heating, no more temperature raising. The heating just vaporizes it. And finally, this is what we're going to do in our demo. We're going to vaporize some water and turn it into steam. And then you can have superheated steam, which is above the boiling point. We can make the steam even hotter. And that's what we're going to make it so hot that it should catch some paper on fire. So that's what we like to see in chems, fires, right? So, room temperature, pure liquid water is transparent, odorless, colorless, and also tasteless. And notice we say pure liquid water because everyone's going to argue that their bottled water has a different taste to it, right? In fact, over COVID, my wife and I got bored. We were like reading the back. Is that an Aquafina bottle over there? Or is that something? Can you see what the ingredients are on that? Because we were bored. We were reading the back. It might have been Dasani, not I think it was Aquafina. One of the companies. We were like, why are they putting all these? There's like sodium phosphate or something. Just different salts. Is there anything on there? So maybe not in that. Let me see. Maybe it was Dasani then. It's probably Dasani. Yeah, this doesn't have it.
This one has
calcium chloride.
Sodium bicarbonate.
Sodium bicarbonate. That's like baking soda. Magnesium sulfate. So there's all these salts in there. And we called up the company and asked them why they had those salts in there. And they said, well, we need to have those salts to maintain our unique taste profile for our water. So I think it's a conspiracy that they're trying to put salt in there to make you thirsty and drink more. But that's just me. But I'm sure. But honestly, to be honest, you do want to have some ions in your water. You don't want to be drinking pure distilled water because then the water is like less concentrated than your body, and it's going to draw water out. So you do want to have a little bit of salt in there. I'm just kind of joking about that, the conspiracy. But who knows? Maybe there is that to some degree. I've heard that about certain waters. But so anyway, that I just said that because people will say water has a taste. Well, they're not drinking pure water, and that's why. Molar enthalpy of fusion is very large compared to other solids, so it takes a lot to melt ice. That's why ice is good for like an ice pack or cooling your drinks, because it takes a lot to melt it. If you had something that melted quickly, why would you want to put not the fact that it's not water? Also, it's probably a bad idea to put in your drink, but you want something that holds a lot of energy that takes a long time to melt. A lot of energy to melt it. Again, water expands in volume, which is why it's less dense and it floats. So water's all good for all sorts of stuff for us. Not even to mention that it's a good solvent that this section doesn't talk about. But the boiling point and the molar enthalpy of vaporization are both very high as well. And this is why steam has a great deal of energy and why you can get burned by steam, because it's holding all that energy that it took to boil the water. To boil the water. So we can look at this, how much energy is absorbed when 47 grams of ice melts at STP, how much energy is absorbed when the same mass of liquid water boils. To know this, we need to know the molar enthalpy of water, and that's something that can easily be found. So I'm just going to Google it. Water enthalpy of vaporization. So notice they give it this in units per mole, or kilojoules per mole. So it takes 40.7 kilojoules to vaporize water. So looking at this, that's in grams. So we can quickly convert that. Let's convert that to moles so we know what we're dealing with here. Are we trained yet? Do we know the molar mass of water? 47 grams. Or has it been too long since we did stoichiometry? Does this number look familiar? 18 grams per mole. Can somebody just real quickly do 47 divided by 18 for me? .6. So 47 grams is the same as 2.6 moles. I think you guys can figure this out. If it takes 40.7 kilojoules to vaporize a mole of water, how many kilojoules is it going to take to vaporize more than that? 2.6 moles. What would I have to do to this number? Well, it would be about, would you agree that it'd be like maybe, yeah, you're saying what I'm thinking here. But I would multiply it, right? I would just take 2.6 times, was it 40 point, I think what was, oh yeah, 40.65. So 40.7 basically. So I just take 2.6 moles times 40.7 kilojoules per mole. You want to do that one for me too, real quick? That sounds about right. So we'll say 106. About 106 kilojoules is how much energy it takes to vaporize that much. That's a lot. And then, how about to melt it? So to find out how much it would take to melt that much ice, we look at the fusion. The fusion of water is 6.01 kilojoules per mole. So I could take 2.6 times 6.01. So does it say 15.6 kilojoules? So that's how much it would take to melt that much ice. That's how much it would take to boil that much water. But there's also, I'm not talking about what's in between. If you're going to go from ice to liquid and then liquid to steam, there's also all the energy it would take to heat it up to the... So if you're looking at that graph, it's going to take some energy to heat it up to the melting point. What we calculated right here at the melting point is how much energy it takes to melt it. Then it takes more energy to heat it up to the boiling point. And then what we calculated here is how much energy it takes to boil it all. And now what we're going to do is look at heating up steam even hotter than that. Does that make sense? So I'm going to get rid of all that. So I'm going to throw a video up here, and we'll do it in person too. We're going to look up superheated steam.
Did you know it's January? A little bit of a play on words there, and that's Jeff Stevenson. Right next to me, he is joining us with some air-related demonstrations. So celebrate January.
Exactly. And what I brought today, Chris, is I brought some steam. Okay? And this is probably what you think of when you think of steam, like on the tea kettle or something like that. But what we're seeing is actually not steam, because that's the air molecules condensing to form kind of like a cloud, right?
Okay.
When you have condensing air molecules, you know, Chris as a meteorologist, that you get cloud formation like that. What really is the steam is the invisible stuff right at the very tip of your tea kettle. That's really what steam is. By definition, steam is invisible. So we're going to see if, and you know, steam is 212 degrees, and we're going to see if this quote-unquote steam is hot enough to ignite a match.
Really?
So go ahead and see if you can't just put it right in the path.
So I have a matchstick
Yes,
there.
and get it nice and close. It doesn't seem to be working, right?
Okay.
And the reason for that is, if you can go ahead and set that down.
So you set me up to fail.
I didn't set you up to fail. I set you up to learn something, Chris.
Okay.
To learn something. Because
Fair enough, Jeff.
this is actually condensing just a lot of water,
Okay.
as you can see. And so we're actually probably moistening that match more than we are.
That's what I was thinking initially when you told me to do that.
Exactly.
All right.
So what I need your help doing is, if you put those down, put on some goggles.
Okay.
We're going to get our blow torches
Goggles.
here.
Okay.
And we're going to go ahead and you're going to kind of torch these bottom three rings. I'm going to torch the top, and we're going to see if we can't superheat this steam.
Fire it up, my friend.
All right, here we go. And now you'll see that some of the water that's collected in the bottom is going to kind of squirt out, but that's pretty normal.
Okay.
And what we're trying to do is we're trying to get to the steam hotter and hotter beyond 212 degrees Fahrenheit, because we want it superheated. And how we'll know that it's superheated is that the steam will no longer be visible. You see how it's
Really?
getting clearer and
It
clearer?
is.
And Now this is the dangerous part because now you can't really see it, but it's actually the absolute most dangerous portion. Get right in there, Chris. Don't be shy.
I'm good after
I
it,
need
buddy.
you to help me here. I need you to help me. We got it superheated.
That's what I did. I was like feeling to
All
see
right.
if there's steam
No,
coming
I'd
out.
say you see it, but you can't see it, right?
I don't, no.
You don't see it. So now we know that we're pretty hot. So if you want to put yours down, go ahead and turn your torch off. I'm going to continue to torch. And go ahead and try a different match, one that we haven't moistened.
Okay.
I'm going to keep it heated. Yep, and put it right up next to it. Ooh, and as you can see, we are actually able to light a match. I wanted to stay on too long, but we are able to light a match. Right? You can try another one if you'd like.
Sure.
Maybe come in from the top. Yes, perfect, perfect. Maybe let's try a piece of paper. How about we try a piece of paper? Still use the tongs. And just put it right up next to the nozzle there. And as you can see, put it right in the center of the paper, right in the center of the paper. Now, it's not going to light the paper, but it is doing that browning, right? We are actually able to burn it, and there's all this invisible steam that's superheated that is igniting our paper. Now, I did bring one more fun item. Okay. Now, normal paper is okay, but I brought you, if you want to put that down, some flash paper. This is like the magician's tool. So if you want to put that down, and I'm going to keep heating this up because I need it to maintain that super hot temperature. All right, and just go ahead and just put it right in the tip there. This is a magician's flash paper. All right, and it just immediately kind of goes away. Isn't that nifty? You want to do it again? I know you do, Chris.
Please.
All right, we're going to use like twice the size of paper though.
All right. Still superheated.
Let me make sure it's superheated. All right, you ready? And 3, 2, 1, put it in. Woo! And it's such cool paper because it's gone before it even hits the table. Isn't that amazing?
Find that somewhere in thin air.
Yeah,
That's
yeah.
cool.
Okay, it's
That's
out there.
science.
Yes.
That's what you guys are all about at the Imagination Station. So, what are we going to get into with January?
Well, January, we
All right, so we don't care about January. It's not January. So, let me pause. I do have homework 10B you can do up there to finish off the chapter.